Using probability to predict. Let's make sure for this lesson that you have your Desmos calculator and your fraction calculator up in a separate window like I've done. And let's dive right in to begin talking about our lesson. This starts me at number 3. I'm going to go backwards to number 1. We've got 8 problems. And number 1 starts with talking about Aiden flipping a coin. It says Aiden flipped a coin 33 times. It landed heads 9 times. Based on experimental probability and written as a simplified fraction, aka get that simplified fraction calculator out, the p head, so the probability that he gets heads is. So notice what it says. It says experimental probability. There are 2 types of probability. There's experimental and there's theoretical. Experimental says, hey, we're going to do an experiment. In this case, Aiden does one. He flips a coin 33 times, lands heads 9 times. So according to the experiment that he did, what's the probability that he got or will get heads? Well, 9 out of 33 is his data. So go over to your fraction calculator that, again, hopefully you have opened up in a new window, and type however many times he got heads on top over how many total times he flipped it on bottom. Hit calculate, and you will get your answer. Number 2 says, based on experimental probability, so we're still using the experiment, if Aiden flips a coin 44 times, he's likely to get blank or heads blank times. So go to your Desmos calculator now, type in the answer you just got, and then multiply that out of the denominator by how many times you flip the coin again, or how many times Aiden does. Because if he gets 3 out of every 11 are heads, then 44 times should be 12 times. So we write 12 there. Now it says based on theoretical probability. So that means ignore Aiden's experiment and just in theory, if he was to flip a coin, what's the probability that he would get heads? Well, in that case, it's just a half. There are 2 sides and one of them are heads. And then theoretically still, if he does that 30 times, then we could take our theoretical probability of 1/2, get it out of our denominator, and multiply it by how many times he theoretically flips his coin. 15. And there you go. Right off the bat, great practice with experimental and theoretical probability. You're going to have different numbers throughout this assignment, so make sure you're using your numbers. If you just got a bunch of red, hit redo. You can redo these problems. Yay! And use your numbers instead of mine. Number 2 is the weirdest looking spinner you've ever seen. Whoever designed this image messed up a little bit, but we will forgive them. Let's assume that these are all equally sized and that this meeting of the sectors or the wedges happens in the middle. Ross spun the spinner 18 times. Estimate the number of times he landed on green. So the first thing we need to do is figure out what's the probability that if you spin it once, you get green. Well, I see 1, 2, 3, 4, 5, 6 wedges, and only one of them are green. So it's a 1 out of 6 chance of getting green, and then you multiply that by how many times Ross spins it. In this case, 18 times. So he should get 3 to land on green. All right, then we do the same thing, but this time we have red. Well, there are 2 red sectors on these 6 sides here. So we do 2 out of 6 times how many times he spins it. In this case, 36. Again, use your numbers, not mine. 12. Okay. And then we've got number 3. Rob rolls a number cube 60 times. The best estimate is that he will roll a 6 blank times. Well, he rolls it 60 times, so we're going to have to multiply by 60, but remember that the roll of a number cube is 1 out of 6 for each of the numbers, and then that he'll do times 60. Or 60 divided by 6, you get 10 either way. Number 4. Sarah surfs with her friends at Virginia Beach. Ah, the good old days when friends could just surf together. Her friend Mark caught 3 waves out of 12 possible waves to ride to the shore. So there's my fraction, 3 out of 12. Remember to use your numbers. They stay out in the water for 24 more waves. So times 24, you get 6. And look what it says. Surfing pun. Cowabunga, dude. It's also a Ninja Turtles. Shout out to Ninja Turtles pun. All right, 5. A professional basketball player practiced shooting free throws before a game. Must be like a center or something, because those aren't very good professional basketball numbers. Resembles what I could do in high school at my very best, though. 22 out of 33. If he does that for 9 more shots or 9 more opportunities, it's 6 of them. And yeah, that's not good for a professional basketball player. You should at least try and shoot 80%. And like the old basketball movie, you've got game, like he got game. Shout out. All right, number 6. Sally drank 66 ounces of water in 8 hours. If she continued drinking water at this rate, she would drink blank ounces of water in 17 hours. All right, so for these last 3 problems, we are going to have to use proportions, which is one of the reasons why we have a proportions and probability book that we're doing this out of. So with proportions, this is sometimes called the fish method or the Band-Aid method or the butterfly method. We're going to separate our different categories. In this problem, we've got ounces and we've got hours. And this equal sign means the difference between one time you do something and the other time. So it said, Sally drank 66 ounces. I'm going to put that with the ounces. In 8 hours. So it's the same time. So I put it below with hours. If she continued drinking water at this rate, so now we're going across the equal sign because we're talking about another time, she would drink blank ounces of water, so there's my X, in 17 hours. This is most commonly called the cross-multiplying method because you take the 2 that are diagonally across, and here comes that Band-Aid, or if you add a head to the Band-Aid, it becomes like a Doug Funny shout-out butterfly. Okay, well, that's horrific. And you see, how do I solve for x? Well, the diagonals, you set them equal to each other. So 8 times x is 8x, and that equals 66 times 17. So, sad me, got a little rabbit situation. We divide by 8. 66 times 17 divided by 8. So a shortcut, if you're still confused out there, I'll just tell you have 3 numbers. Take your largest 2 numbers, 66 and 17 for me, multiply them together, and then divide. And you can do that like this. You can do it like this. It does not matter. PEMDAS will take care of the hard work. Your small number goes on bottom. You could get a decimal, but it shouldn't be a really long repeating one like I had before with the free throw problem. Instead, it should be like 0.5, 0.25, something like that. And I wish it said, like, you're hydrated. Instead, it just says fantastic. But there you go. Number 7 is the similar problem. We've got townspeople and we've got middle schoolers. So we've got middle schoolers and townspeople. 820 townspeople were interviewed at random. 40 of the interviewed townspeople were from the middle school. So 40 out of those 820, so I put them above each other. The middle school, so that goes in top, has 760 students. So cross, multiply, and divide. I'm going to once again multiply my big 2 numbers times each other, 820 times 760, and then divide that by my smaller number, 40. I'm going to get a big number, but that is to be expected because you're finding out the population of the whole town. Let's get rid of some of these that are starting to build up. Now I'm going to do the slash first because I just like how it looks, but it's up to you. 820 times 760 divided by 40. 15,580 people in that town. And we never ever use commas. Just put in your numbers. And the final one. The Coast Guard was concerned about the growing number of harbor seals in La Jala, or as I like to say, La Hala. They tagged 20 seals and sent them back into the bay. After 2 months, they checked a sample of 49 seals. 5 of the seals of the sample were tagged. The Coast Guard estimated that there were approximately blank seals in La Hala. As fishy as this problem sounds, it's very sound logic. You cannot interview a whole town or interview find every seal. So you really do. This is a very practical statistic situation for all these problems where you just take a sample and then you try and like apply that to the whole. So in this case, you tag 20 seals. So we've got tagged seals, and then we have, I'm just going to call them seals, total seals. So they tagged, that goes in the top, 20 seals, sent them back into the bay. After 2 months, so they don't give you how many total seals, this we have to solve for, so I put the X there. After 2 months, they checked a sample of 49, so that's under general seals, and 5 of those, so I put it above the 49, were tagged. So once again, we cross multiply and divide. Multiply our two large numbers divided by our small number, and we will get our answer. So let's do that. I can even just replace the numbers up here. I've got 49 times 20 divided by 5. 196 seals. Sealed it. Nope, didn't say that. Or like SEAL Team 6. There's no SEAL puns here. Alright, that was using probability to predict. Once again, kind of a nice, easygoing assignment. Looks like I started this before lunch, so it took an hour and 30 minutes. I missed last time that it took me like 120 days from when I'd opened that one. Or maybe that was 2 assignments ago, so anyway, sometimes it just says that. But it took us a little less than 11 minutes, I think, total, so good for you if you got this done. If not, keep working at it. I believe in you. You got this. And I will seal you next time. See what I did there? See what I sealed there? Okay, I'm going to stop while I'm behind. See you later. Have a good day. Dylan out.